Alright, so in this lesson we're going to look at kinetic energy and how work plays a role in determining kinetic energy. So the first thing when we start talking about kinetic energy is we've got to define what kinetic energy is, and kinetic energy is the energy that's associated with the motion of the object. If you ever see the word kinetic in physics, it's talking about motion. The most common type of kinetic energy that we'll deal with in this section is that top one, translational. This deals with side-to-side motion. We'll also get to rotational kinetic energy a little bit later in the term. It's also worth pointing out that you can define what's called vibrational kinetic energy as well. We won't get to that, and we might get to that toward the end of this course, maybe not in this course. Now, translational kinetic energy can be fairly easily calculated. Kinetic energy is half the mass of an object times its velocity squared. Now it's worth pointing out that kinetic energy is a scalar. When you do V times V, you ultimately get a scalar out of that, and so you get 1/2 mv squared as the kinetic energy of an object. So let's look at changes in kinetic energy. There are two ways that kinetic energy can be changed. The first one is the mass of an object could be changed. A situation where this could be occurring is you have a let's say a big pickup truck, and you're throwing bags of rocks or sand or whatever out of the pickup truck as it's moving. So that's an example of where the mass of the object changes. The second one, which is more common, is that the velocity of an object can change. So if we think about how the velocity of an object can change, net force causes acceleration, which changes velocity. So if the velocity of an object changes, that means that a net force must be acting on that object. So net forces also change kinetic energy. Well, if we remember back from the previous unit, net force does work, which has the same units as energy. So how are work and the change in kinetic energy related to one another? So here's what we call the work energy theorem. Basically, how work and change in kinetic energy are equal to one another, and what it basically says is the work done on an object is equal to the change in kinetic energy of that object, or on that object. So work is equal to change in kinetic energy. Now this is a kind of simplification of what's going on. It's probably more accurate to say work is equal to the change in energy, but for the sake of our problems here, we're going to think of work as equal to the change in kinetic energy. So work is equal to 1/2 mv final squared minus 1/2 mv initial squared, or we could think of it as F times x is equal to 1/2 mv final squared over 1/2 mv initial squared. If we rearrange this, max, since F is equal to ma, and if we divide everything by m and multiply by everything by 2, what we get is a familiar expression. This is actually the last of the toolbox equations. So the last of the toolbox equations is ultimately a statement of the work energy theorem. Here we go. So let's do a quick problem. Here we have a deep space probe. It's launched on October 24th, 1999. It's called Deep Space 1. It's used a type of engine called an ion propulsion drive, and the probe has a mass of 474 kilograms and is traveling at 275 meters per second. The only force acting on the probe is the thrust of its engine, which it says is 5.6 times 10 to the negative second newtons, which is actually a pretty small force for something that's 475 kilograms about. That's like hitting it with a BB, once a second is probably that type of force. The impact of a BB on this space probe. The force applied is applied over the distance of 2.49 times 10 to the 9th meters. That's 2 million kilometers. So this is a long distance that this probe has been experiencing this very, very small force. So once it's determined the final velocity of the probe, assuming the mass remained constant. So here are the known pieces of information: the mass, the force, the distance traveled, and the initial velocity. The unknown is final velocity, and the relationship I'm going to use is the work energy theorem. Fx equals 1/2 mv final squared minus 1/2 mv initial squared. So let's do some math. The first thing I'm going to do is add the initial kinetic energy over to the left-hand side of the equation. You divide everything by m, multiply everything by 2 to get rid of the 2 or the 1/2 m on the right-hand side, and then you're going to square root everything and get that the final velocity is equal to 2 times force times distance traveled divided by m plus initial velocity squared. So if we do my calculation, I get the final velocity of this object is 805 meters. So if I apply this very, very small force over a very, very large distance, I get a fairly decent change in velocity as my final change. So that's kind of a quick application of the work energy theorem and how we can use that to begin to solve a problem dealing with work and energy.